Hi, my name is Steven. This is Lab6Group2a, and this is Lab6 off-axis aberrations. So here's a basic setup here. We got a spatial filter and a collimating beam. Together they make our beam expander. We also have an objective here. We had some problems with our objective this time around. It wasn't giving us the cleanest beam that we wanted to, but we were able to get a semi-clean beam to get through this system. So after the collimating lens, we have the fold mirror here, and that shoots the light to our Hartmann mask. And Hartmann mask is different than last week's mask. Instead of having holes across the center, we have two holes on either side, on the left, right, and top, bottom, and a hole in the middle. So what we did for our test here is that we shoved the light through the center hole and found our reference point. After we've done that, we wanted to measure some off-axis aberrations. So how we did that was we moved this mirror here along the z-axis, and then we shot the light at a different angle, so it simulated an off-axis point. Once we shot the light through, say, we would block each side of the Hartmann mask with this hole blocker, very high-tech. So we blocked and we shot light through. Then we had to go through our microscope, and our microscope measured the epsilon y offset that we had. As you can see, we had a pretty difficult time measuring because the line was on the bottom, so we had to double mirror it all the way. Just a side note, we originally thought, why would we want to maximize spherical aberration when we're trying to measure a coma? What we concluded is that when you have a maximized spherical aberration, you have a pretty good coma aberration too. If you minimize the spherical aberration, having the plano-convex lens is the way to minimize spherical aberration, then you're actually getting not a lot of coma. You're not minimizing coma, but it's close to zero in that case. So for different parts of the lab, we wanted to measure the aberrations at different points along the field. How do we accomplish that? Well, we found our 0 point initially, and then we moved it a certain distance away by turning this Y micrometer. We personally did 5 twice, -5 and 3.5. That corresponds to a full field of from -1 to 1 and then 0.65 field.
Hey, my name is David Montgomery, and for part C of the lab we measured coma. As Steve mentioned before, we already put it off-axis, and that's kind of a key point because coma is an off-axis aberration. To start it, we use these mini aperture holes, and for coma we basically want to block out 4 out of the 5 holes. So for the first test, we take this hole and block out either the left or the right, and then just move the Y translation for the microscope. And as we moved the Y translation, we basically just had to look at this viewing screen and had to make sure that the virtual image of the reticle was aligned, or we could see it. And we did this 4 times with 4 holes, excluding the center one. And basically we compared either the right or the left, or the top and the bottom, as to what changes in the distance in the Y translation was made when we tried to find the reticle on the viewing screen. For the next part, we looked at astigmatism, and for that one, we basically just had to block 3 out of 5 holes, either going all the vertical holes or doing all the horizontal holes. So 2 measurements were taken with that, and that worked a little bit differently because we actually had to use the Y and the Z translation stages of the microscope for that one. And basically what we wanted to do on the viewing screen, the Z translation was basically to get it at best focus, and that was made by taking the 2 circles and making sure it was aligned along the reticle, and then of course we moved this so we could, the Y translation, so we could find the reticle on the viewing screen.
Action.
Alright, so you can see for these values right here, this is our coma section. So we use 1 point at a time, or 1 point at a time for these. And so you can see the equations below. You can see a slight variation, just a constant variation between the 2 different comas. And so we took 2 points, and then we took the average to find the value of what W131 would be. Over here you can see our values. They're not very consistent, and they don't really make that much sense. So we probably had some problems in our lab, some errors. We've talked about some of those already. And so then we moved on to our astigmatism here. And so we took measurements of 2 points at the same time, and we found delta z and delta and the change of the epsilon y. And so using defocus and astigmatism, we should be able to find the value of W222. And so, from what we know there'll be a value for the y, and there won't be any values for x. So you can see over here, we have no sagittal values, and then we're going to have some values here. The astigmatism values kind of make sense because we know that when there's spherical aberration in the system, there won't necessarily be uniform throughout. One problem is we should probably have a negative value somewhere in here, and we don't. That's all.